Good morning. I hope I'm audible to you all.
Yes, ma'am.
Okay. So in the last class, we were talking about Bravais lattices, and I explained what is a Bravais lattice. Those are basic structures where all the lattices are equivalent. Okay, and we're talking about lattice, not atoms. All the lattices in the Bravais lattice are equivalent, and basically there are seven families or seven class of structures: triclinic, monoclinic, orthorhombic, tetragonal, cubic, trigonal, and hexagonal. And within them, in some cases, you have three or four lattice types are there. And this table, each of you should know. And these classifications are done based on the axial relationship, meaning A, B, C, their lengths and their angles. Okay, and these figures also you will have to know for the examination. By the way, I just need to tell you something. On 27th, you're going to have your first test. Okay, on 27th, you have your first test, and the syllabus will be chapter number 1 and 3. Chapter number 1 and 3. 2 is, when I'm saying 1 and 3, it's of the book. I have shared with you the textbook also, soft copy.
Okay.
Yeah. Now going ahead, so this is the summary, the number of lattice points per unit cell, etc. There is one thing that you might not have heard about: simple cubic, body centered, face centered. You've heard there is something called base centered also. So what is this base centered? Let us see. So when you are talking of base centered, let's say we are talking about a structure like this, a Bravais lattice. Then there may be lattice points at all these corners. And additionally, on the base here, you have a lattice point. Similarly, here, you have a lattice point. Because this becomes a base for another cell here. Similarly, this becomes a base for this particular cell. Okay, and here when you see what is the total number of atoms, it will be 1/8 from each corner and half from the two bases. So that will be 2. Okay, this is one additional thing that you might not have noticed previously when this was taught in the other subjects. Now from here, let's quickly move to indices. See, what happens is when you are doing crystal structure and when you want to relate it to properties, then what happens is you will find that many of the properties are going to be dependent on the direction of the crystal. The position of the atom and their directions will give you a lot of information about what is the property of the given material. So what happens is we have to now see what is the meaning of lattice direction and lattice plane. So basically what you will do is you will use 3 numbers and index a direction. Similarly, you will use 3 numbers and index a plane. Let's look at this. You have a cube, for example. You can see the x-axis, y-axis, and the z-axis. Please use your laptop, only then you can see the x-axis, the y-axis, and the z-axis. And here you are shown, obviously, you can see what the origin is going to be. The origin is going to be this, okay? And you're shown a number of arrows: 1, 2, 3, 4. And you're finding that, we are giving some indexing for each of this. Like, for example, from this corner of the cell to this corner of the cell, if you have a direction given, how do you index it? Similarly, from this corner on this face, from here to here, how do you index? Then from this point to this, from this point to this. So basically, I've given you some 4 arrows and you have to know how to index or give the lattice direction. So what do? First of all, draw a vector along or parallel to the desired direction from the origin. From the origin, okay? So that means these three black arrows are qualifying for what we have said. The 3 are drawn from the origin. Then after that, what do? You have to write the component of the vectors. You have to write the component of the vectors in terms of x, y, and z. So what we'll do is we'll take this one, for example. If you see that this vector has x component equal to 1, y component equal to 1, z component equal to 1. Because it is connecting the two opposite corners. Okay, so that means this is a vector which is having x, y, z component and it is within that unit cell. Therefore, you can say that the components of this vector, this directional vector are 1, 1 and 1. So what you do is you put it in a square bracket. Okay, and what you get is going to be the index of the lattice direction. Now let us try another one. So look at this direction, this arrow for example. This arrow is lying on the base of the cube, on the base of the cube. So what we can do is, you can see that if I extend this cube behind, this direction is going to look like this. Okay, and if I try to see what is going to be my x, y, and z components, I find that the x component is going to be equal to -1. X component is going to be equal to -1. Y component is going to be +1. And the z component is going to be 0. There is no component along 0. So what you have to now do is, you have to write this as in a square bracket 1 bar 1 0. 1 bar 1 0. So that is the direction. Well, actually it's 1 bar 1 0. And similarly, let's come here. This particular arrow. I'll use another color. If I'm talking about this particular arrow. Okay, it is lying on the base. It is lying on the x and y plane, xy plane. So you can see that it has got x component 1, y component 1, and it is not having any z. So it is 1 1 0. Okay, now similarly, let's go to this red color arrow. This red color arrow here. Okay, so what we'll do is we will translate it so that this edge is coming to the origin and then try to look at what are the components. You will find that it is going to have a -x as the x component, -1 as the x component, and y component will be 0 because it is lying on the xz plane. And z component, again, it is not plus z, it is going to be -z. Look at the direction of the arrow. So it's going to be -1. So when I put it in a bracket, it will be 1 bar 0 1 bar. I am not going to talk more than this because the book itself is only talking this much about it. Okay, so if you have vectors given to you, reduce it to the smallest integers of the same ratio and write it within a square bracket. So that gives you the lattice directions. SPM, you've already done it. So I'm just going to touch as much as the book wants us to do it. Next, let us talk about indexing of a plane. Like for example, I have, let's say this is a cell, and I may be talking about a plane like this. This may be the plane I'm talking about. Or I may be talking, this may be the plane I'm talking about. So I need to index the plane. So what do we do? Once again, you have to show your x, y, z axis, and then your origin you have to fix. And then what you have to do is the intercept that the plane makes with the crystal axis. Crystal axis means x, y, z. You have to find the intercept that the plane makes with the crystal axis. Like for example, this plane is cutting the axis at 1 1 1. It's cutting at 1 1 1. Then what do? Get the reciprocal of this. Get the reciprocal. So what you have to do is, first you have to get the, where it is cutting the XYZ. So in general, you call it as PQR. In our case, it is 1 1 1. Next, what do? The next step is get the reciprocal of PQR. Reciprocal of PQR will be 1 by P, 1 by Q, 1 by R, which is going to be equal to H, K, and L. So if I do this here, 1 1 1 simply becomes 1 1 1 only. The reciprocal of 1 is 1. Okay. And after I do this, what you have to do is write it in terms of integers of the same ratio. Sometimes you may get fractions. So what you should do is convert it into integers of the same ratio. In our case, we don't have to do all that. So just write it like this, 1, 1, 1 with no commas in between. So that's the index of that red plane that I have shown. Similarly, let us take another example. This is my origin. This is y. This is my x. This is going to be my z. So let me talk about a plane. The plane I'm going to talk about is this. If this is the plane I'm going to talk about, then look at this. It is parallel to which plane? This green marked plane is parallel to which plane? XY, YZ. Yeah, YZ. It is parallel to the YZ direction. So that means it is going to cut only the x-axis. So it's going to cut only the x-axis. So the intercept is going to be 1. It is not cutting the y and z. So the intercept is infinity and infinity. Okay, next what I do, I have to get the reciprocal. So 1 by 1, 1 by infinity, 1 by infinity. So that becomes 1, 0, 0, put in curved parenthesis. So this is how you do the indexing. Similarly, one can also, for example, okay, maybe if I'm talking about an intercept which is negative, if an intercept which is negative, then what you should do is you have to put a 1 bar. A bar you have to put if it is negative. So let's just go to the next picture. So here are some pictures given to you. Okay, like for example, yeah, this is 1, 0, 0, which we just did because it is parallel to the YZ plane. Now let's look at another plane here. So this will be 0, 1, 0. 0, 1, 0 because it is cutting at 1 at infinity, 1 and infinity. So the reciprocal becomes 0, 1, 0. Okay, let me now ask you one question. What would be the index of a plane like this? Parallel to 0, 1, 0, but which is cutting it at half. Anyone? It is parallel to 0, 1, 0, but it is cutting the cube into half. Anyone?
0, 2,
0, 2, 0. It is 0, 2, 0 because the intercept will be infinity, half and infinity. Take the reciprocal, it becomes 0, 2, 0. Okay. Similarly, you have 1 bar 0, 1. 1, 0, 0 and 1 bar 0, 0 are going to be parallel planes. They're going to be parallel planes. Like for example, if I'm talking of 1, 0, 0. Okay, so this is my 1, 0, 0 plane. We already marked. Okay, so 1 bar 0, 0. Where will it be, you think?
on the other side of the x-axis.
The other side, on the other side, and they will be parallel to each other. They will be parallel to each other. Next, similarly here we are shown something else also. 1, 1. Okay, let us take this one. So a plane that is going to cut like this. Okay, you can see the intercepts. The intercepts are going to be 1, 1, infinity. Take the reciprocal, it will become 1, 1, 0. So that's your 1, 1, 0. Now, take another parallel plane which is cutting the intercept parallel to 1, 1, 0, but then cutting the axis at half and half. Therefore, it is 2, 2, 0. 2, 2, 0. Instead, take another plane which is going to cut
1 by 3.
into three parts. Okay, therefore it becomes 1 by 3, 1 by 3, infinity. Therefore, 3, 3, 0. And one thing you will be noticing here is that as the numbers are going up, you're going to find that the distance between the planes becomes smaller and smaller. Are you noticing that?
Yeah.
Because 1 is the size of the unit cell. So what happens is when this number becomes larger and larger, you are actually, the intercepts are fraction. So it becomes closer and closer. This idea you're going to need in the forthcoming chapters. That's the reason why I'm just trying to make you understand it. And in the test, you can expect these kind of small questions. And
will the test be written or MCQ?
It will not be MCQ. Let's not have it MCQ, because if you really want to learn something, let's just do away with MCQ. MCQs, I am thinking of giving 2 quizzes for about 6 marks, so that, you know, some marks students will get. But then only if you write a written test, you people will learn something.
The written test will be open book or proctored?
It will be proctored. We don't mind open book. We don't mind open book. What we mind is you people copying from each other.
Okay.
Or from the internet. You can use your material. It will be proctored. You can keep your cameras on, and then, you know, we'll allow you to refer to your material, your own material. That's not a problem.
Okay.
So now let's go to, but of course, there may be some limitations on that also. Let me not promise anything. Okay, now let's go to some common crystal structures. Simple cubic, I don't have to teach you at all. Polonium is the only metal which is a simple cubic. Most of the materials don't like becoming simple cubic. Only polonium is an exemption, and you find that the total number of number of atoms, here we are putting the atoms at the lattice space. Till now, we talked about Bravais lattice. When we talked of Bravais lattices, those positions were occupied by lattice points. But now we are talking of crystal structures. Are you able to see the difference between the two? When we talked about a cell, and when we were talking about a Bravais lattice, we had some structure, but the corners or whatever positions were occupied not by atoms, they were occupied by lattices. And the lattice itself could be having more than one atom. The lattice itself can have more than one atoms, or it can have only one atom. That can change. But now we are talking of crystal structure. When we are talking of crystal structure, we are going to talk about cells where the positions are occupied by definite atoms. Are you able to see the difference between the two? Bravais lattice and a crystal structure?
Yeah.
Right. So now we're talking of crystal structure. So the number of atoms, it's a primitive cell. Straight away you can see it's a primitive cell because there is only one lattice point associated with it, and there is only one atom associated with this particular cell. So you have to remember that, you know, a primitive cell will have only one lattice point associated with it, but it can have more than one atom associated, because a lattice point itself can have sometimes a cluster of atoms. That is a basis I've talked about. Now let us go to cesium chloride structure. Cesium chloride structure, if you see, you are having a cesium at the center of this structure. Chlorine is occupying the geometric center, cesiums are occupying the 8 corners, or it can be the other way also. Because after this is one cube, you can have a cube here where the structure is just the opposite. But then the entire thing will give you cesium chloride only. Now, don't be tempted to write this Bravais lattice as BCC. This is not BCC. Okay, this is not BCC. Why is not BCC? Can you tell me? If it was a BCC Bravais lattice, what should have happened? Every lattice point should have been occupied by the same basis. Yes or no?
Right. They're different atoms.
They are different. So definitely this is not BCC. Guys, please listen. This is not BCC. This is a simple cubic. Then you will ask, if that is the case, then how are you going to explain this, the presence of this new fellow chlorine sitting here? So this is what you have to now do. You have to cluster these two, and this becomes a basis. Okay, cluster these two, and this becomes a basis. So your basis is going to have two different atoms, one located at 0, 0, 0, and another located at the center of this crystal, which is half, half, half. Are you understanding this? This is your basis. Then you will say, but then where do you see such basis for the other guys? You are seeing for the others also. Like, for example, if I am talking about a cell here on top of this, so this fellow is going to have
A chlorine atom.
here. So this will be the basis. Similarly, because it's an infinite structure, you can keep thinking of this kind of stuff. So each basis becomes a lattice point. And if you look at the number of lattice points for a cell, it is just going to be 1. So it is simple cubic. Did you understand this point? Yes or no?
Yes.
See, this is your cell. You have cells above, below, in front. You have so many cells like that. Okay. So you're taking a point here and talking about a basis at one chlorine at the center, and we are calling this a basis. Similarly, an atom here will have a basis here. An atom here will have a basis here, here. So all of them will be having basis. So associated with every lattice point, there is a basis consisting of one chlorine and one Cl. So the structure is not BCC, the structure is simple cubic. So these are some mistakes that your books would have made in your school level and your preliminary level and all that. Once you come to crystallography, you have to unlearn all those mistakes. Now let us look at the crystals of alkali metals. This is another structure. So now look at this. The structure is BCC. Structure is BCC. Okay. And look at this. This is an alkali metal. Now you will say, why are you saying the structure is BCC? We are talking of alkali metal. All the lattice points are equivalent. They are going to be occupied by the same atom. So the structure is BCC. So your conventional structure and your this structure, it become, I mean, your crystal structure and your Bravais lattice are going to be the same in this case. Now look at this. This is one cell, second cell, third cell, fourth cell. Four cells are shown to you. And you can talk of non-identity positions of the atoms. The positions of the atoms are at 0, 0, 0 and half, half, half. 0, 0, 0 and half, half, half. So this is your 0, 0, 0. This is your half, half, half. BCC. Okay. And this is a non-primitive unit cell because the number of atoms associated will be 2. Okay, but then the basis is going to be only one atom. Every lattice point is going to have only one atom. And if you see the number of nearest neighbors, look at this body center, it is surrounded by 8 corner atoms. Therefore, the coordination number is 8. Now, let us look at the primitive cell. This is certainly not a primitive cell because there are 2 lattices associated with one cell. Therefore, you can draw the primitive cell. This we have already done at the beginning of this chapter. So, from one of the corners, connect to the 3 body centers. Connect to the 3 nearest body centers, and these become your A, B, and C. These become your A, B, C of the primitive cell. The angle between them is going to be 109.28. And the edge meaning A equal to B equal to C will be equal to root 3 A by 2. I'm writing different A's. This A is the primitive cell A. These are vectors. Okay. But what is this A I'm writing? This A is the edge, the length of the edge of the non-primitive unit cell. I again repeat, alkali metals take a BCC structure. Bravais lattice and the cell are the same in this case. The atoms are occupying 0, 0, half, half, half position. Because it is non-primitive, we can construct a primitive. How do you do that? By connecting a lattice here to, or an atom here to the body centers, the 3 body centers, 3 nearest body centers. So this ABC that you have drawn now become your sides of the primitive cell. Now, if you connect it and finish it, what you get is going to be one primitive cell. It is going to be a primitive cell. Now, what are these A, B, C? A, B, C are the primitive lattice vectors. These primitive lattice vectors will be having a length under root 3a by 2. And what is this A? A is the side of this unit non-primitive BCC unit cell. And the angle between the primitive vectors A, B, and C will be 109.28. 109 degrees and 28 minutes. Clear to you? And what are the other materials which can? All the alkali metals. So you can just remember your periodic table. All these will become BCC only. You'll wonder, why should we bother about all this? You need to bother about all this because if you're going to work on materials, you need to know what kind of solids these will form. Similarly, let us go to another class on the periodic table, that will be noble metals. What would be the structure that noble metals normally take? It will be FCC. FCC. So here is your FCC. On the face, on each of you have 8 atoms sitting at the corners, and they're all identical. So the Bravais lattice will be the same as your crystal cell. So at each corner, 8 corners, you have 1 by 8, 1 by 8, 1 by 8. Then on each face, there are 6 faces, right? There are 6 faces. On all of the 6 faces, you're going to have an atom sitting. And they will be contributing half to this cell. So therefore, you'll find that this is a non-primitive unit cell. And if you try to see how many lattice points or atoms, both are the same in this case. So there are 4 lattice points or atoms associated with this crystal cell. And each lattice has only 1 atom. So the basis is only 1 atom. Coordination number, if you take, you will find that each atom will have 12 neighbors. Every atom is going to have 12 neighbors. Now you can draw a primitive cell for this. Because it's non-primitive, we can draw a primitive cell. So as usual, take a corner and then connect it to the 3 nearest face centered, not body centered now, because it is FCC. Connected to the 3 face centers. This, the closest face centers. Okay. So once you connect, what you get is going to be your A vector, B vector, and C vector of the primitive cell. And if you try to see how that relates with your cell A, the length of the crystal cell A, you will find that primitive A equal to B equal to C will be equal to A by root 2. And what will be the angle? The angle will be equal to 60 degrees. Angle will be equal to 60 degrees. Okay, now next we will go to another structure called the NaCl structure. NaCl, look at the examples. Other things that can form NaCl structure are KBr, NiO, PbS, etc. So now you're finding that the basis is not going to be just, it's not going to be one single type of atom is not creating the structure. So how do you understand the structure? You have to understand the space lattice as FCC. FCC with chlorine occupying the lattice points. FCC with chlorine occupying the lattice points. What do I mean? FCC with chlorine occupying the lattice points. So the 8 corners, then the 6 face occupied by chlorine. Okay, and you will find, so this would be the structure. Okay, and the positions of the atoms in the unit cell for chlorine and sodium you can always identify. Okay, these are your sodium, These are all your sodium. Okay, so the structure for this is FCC with Cl occupying the lattice points. Then what would be the basis in this case? What would be the basis? Which of the pair of sodium and chlorine should you take together and call it a basis and then call this structure as an FCC structure? You have to put together a sodium and a chlorine separated by root 3A by 2. What is A? A is going to be this. This is your A. Root 3A by 2. So which of those you think it will be? Root 3A by 2. Anyone? So identify one chlorine and one sodium separated by root 3A by 2. That is the basis. Can any of you do that?
Any one corner atom with like the center.
Any one corner and the center. Because the body diagonal will be root 3A. Half of that. The body diagonal. I hope you are understanding what's the meaning of body diagonal. If I have a cube with me, let's say this is my cube. The body diagonal is this to this. That is body diagonal. Face diagonal is this to this. This is face diagonal. So if you look at the body diagonal length, it has to be root 3A. Half of that is going to be root 3A by 2. So it's going to be one one corner and one at the geometric center. So this way, if you try to reproduce all the FCCs, what you get is going to be your NaCl structure. Coordination number is 6. Then let's quickly see close pack structures. This you people have studied in your previous courses also. So here it's actually the hard shell model. So what happens is it's imagined that the atoms will pack themselves in such a way that the nearest atoms will be in contact with each other. The nearest atoms will be in contact with each other. Like look at this. These two are nearest atom. What is lying along this is actually a BCC cell. And you're finding that along the diagonal, they are in touch with each other. Around the side, they are not in touch with each other. So when you stack it like this only, they form a closed structure. And the packing fraction will be the volume of the total number of atoms divided by the volume of the cell. So if A is the side, A cube is the volume of the cell. And if I say that R is the radius of the atom, then it is 4 by 3 pi R cube into the number of atoms associated with that cell. I'm sure you people remember this. Volume of one atom into the number of atoms associated with that particular cell. The number of atoms could be 1 if it is simple cubic, 2 if it is body centered, 4 if it is face centered. So depending on that, n will change. That divided by the volume. Yeah, next. So based on this, you can talk about the packing fraction. This is packing fraction. Packing fraction will be 0.74 for FCC and for HCP, hexagonal close pack structure. Now, how do you get your HCP structure? HCP, so what happens, this I don't have to really talk much. You're talking about putting hard spheres on a plane, call that layer as A, then over that put another layer. You have to put it in such a way that you have to place the second layer B in such a way that the B will go and occupy these depressions of A, these depressions. Then you put a layer C, and where do you put that? You put that in the above the B layer, occupying these depressions of A. Okay, then what you get, this ABC layering that you get will be called the hexagonal close pack structure. Whereas if you're talking of, ABC will produce FCC structure. Okay, and AB will produce HCP structures. And if you look at what is going to be the coordination number, it will be 12. And you can see that the packing will be essentially, the packing fraction will be essentially the same for both of them. Since I am just repeating what you have already studied, I'm not going to talk much about it. Okay, so this is how it looks. You can just go through it. Don't bother, I just left some questions for you. Just go through that. You can see the ratio of C by A. I hope you remember what is C by A for a HCP. So talk about one hexagonal here, a similar hexagonal here. Okay, then this becomes your C and this becomes your A. C by A ratio, it should be 1.633 for HCP. Then HCP, what is the packing fraction? Packing fraction will be 0.743. It is highest for HCP, hexagonal close pack.
Your iPad is at 92%.
Okay. So the packing fraction is 0.743, not only for HCP, it is also the same for one more structure, that is FCC. See here, I've just summarized everything. Simple cubic is the most loosely packed structure. It is 0.52. BCC is 0.68. Diamond is the most loosely packed. That is the reason why, in the case of diamond, structure is normally followed by your graphite. It's so less dense and, it just slips. Now coming to diamond structure. What is there in a diamond structure? Diamond structure is an FCC. Okay. How do you say it is FCC? All atoms are the same. Then why do you call it an FCC? It is a combination of two FCCs. Diamond structure will have FCC symmetry, but then it will be a combination of two FCCs with one displaced from other along the body diagonal by 1/4 of its length. This is one FCC. Then you have another FCC moved so that along the body diagonal, the distance between the two corners will be 1/4 of its length, 1/4 of the body diagonal. And if you try to see the placement of the carbon, for example, in this diamond structure, the 0, 0, 0, they are talking about the base structure. 0, 0, 0 is the base layer. Then above that layer, and then of course, 0, this, 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 this. So 5 of them are sitting at the base. The next is going to be, you have to imagine this cube to be made up of 4 little cubes. Then at a distance quarter from the base, you're going to have this and this in the opposite cubes at the bottom 1/4 of the opposite cubes. Or better still, what you do is you imagine your cube to be divided into 8 equal portions. So there are 8 little cubes. Okay, the base is going to be 0. Then this layer is going to be half. This layer is going to be 1. In between this is going to be 3/4. In between this is going to be quarter. Okay, so keeping this in mind, you look at this. The base is 0, 0, 0, 5 positions are there. And then imagine the 4 lower 4 tiny cubes. Take alternate cubes. Center of the alternate cubes are occupied by this quarter and quarter. Then after that, go to the border of these 4 cubes at the bottom and 4 cubes at the top. Go to the borders and at half, and half, you're filling, you will be filling the one more position. And then above this, you have 4 tiny cubes. Then you put in quarter 2 diametrically opposite. When you come to the top, in the other 2 diametrically opposite, you put at the center 2 atoms. Okay, so that will be 3/4 and 3/4. So this is how your diamond structure is formed. It's a very, very loosely packed structure. Therefore, the packing fraction is just 0.34. I'll do one thing. I'll just remove some of this kachra so that it's not confusing. Yeah. So here is a picture. And what are the materials that will follow this? All the soft materials. Of course, diamond, the reason why it is hard is something else. Your grade tin, germanium, silicon, they are all having the structure. The next is going to be zinc blend. Zinc blend is similar to diamond, but then there are two FCCs. I told you the two FCCs are separated from each other by quarter of a body diagonal. But in the case of zinc blend, what happens is Zn and S. One FCC of Zn and another FCC of zinc. When they come together, you get zinc blend structure. Here I put for you the zinc blend structure. Okay, I try to show the position of the atoms, the layering. So we are actually finishing off this chapter now. All the discussions in this chapter are assuming ideal crystals. We are assuming that you start the placement of a lattice at one point throughout the volume of the material, it is the same. That's what we are assuming. We are assuming this entire material is one crystal. But then in SPM, you have studied that that is not true. All materials will have defects. They will have imperfections. And you know that if I give you a small block of sodium chloride rock salt, it is made up of a number of crystals actually. Okay, so these are defects and imperfections. So what happens is many things that you have discussed in this chapter may not really be completely true when you go to actual materials. Whatever we discussed here, do not take into account the defects, impurities, interstitials, all those things are not taken into account. But then these imperfections have a lot of value. They decide ultimately the property of material. To give you an example, when you add carbon to steel, to iron, you get steel. And you know that how the mechanical property of that material gets strengthened. Slips are arrested. That's what you studied. In SPM, you studied that slips are arrested when carbon is added and it goes and sits at the interstitial positions. So imperfections actually have a lot to do with the properties of material. But since this chapter is the crystalline nature, getting to understand the basics of the crystalline nature of material, we don't consider impurities and such discussions here. Okay. So I am stopping here. Anything you want to talk? I'm telling you, this is the simplest of chapters. It will get progressively difficult. Unless you then and there study, it's going to be difficult for you. And I see that many of you didn't even realize that I have already put the material for you. So what I will do is, I will give two sets of material. One where the writing, is this writing going to be disturbing for you? All this with the pen, whatever I am writing there, is it going to be disturbing for you, or is it okay to keep it there, or will it help you?
Right now, it's not disturbing.
It is not disturbing. Okay, because the writing should actually, if you're attending class, that writing should make you remember, yeah, she said this and that's the reason why she wrote it. Actually, it should help you. So what I'll do is, in that case, I'll just share it as it is. Okay, so recording, I don't know how much it is useful, but since we are asked to record and give it, and recording. But then please tell your other two friends, they are not at all coming to the class. It's going to be very difficult for them to get a grade this semester if it continues this way. 7 courses are there, all of them pretty tough. Anything you want to say?
Should we refer to the textbook also, like along with this?
Yeah, so what I am doing is, because I know which part of it is actually can be consumed by a BSc student. So what I'm doing is I'm just taking out those things and doing. If you simply read it, it may be tough for you.
Okay.
Okay, I'm just giving it to you as a reference. You can once in a while go through that. Go through it, because for some continuity, you can just go through it.
Okay.
Okay. And in some chapters, what I am intending to do is I'll try to take some material from outside also. Whatever is simpler than what is given in the book, I'm trying to do that also, so that you can go through that and learn the subject at the same time. I hope this particular chapter, what was important is to understand the difference between a crystal structure and a lattice structure, Brevis lattice. Did you get that difference?
Yeah. Crystal structure is the actual structure of like that.
Yeah, putting the atoms there, and whatever we discussed all this time, they're all that. But the lattice and the Brevis lattice structures, those are different. The next chapter, what we'll do is we'll be talking about something called reciprocal lattice. Reciprocal lattice will be, you're talking of a lattice which is not actually true, but then a lattice which is going to be so important all your life. Like, for example, your MRI. You know what is MRI? Magnetic resonance imaging.
Huh.
When you go to hospital, they take the MRI image. You must have seen at least the photos of those. Okay, there also what happens is, you will not be looking at the normal space. You will be talking in terms of the reciprocal space called the K space. So K space is a difficult concept, but then nevertheless very important concept. An analogous thing that I can talk about K space is going to be frequency and time. Time is real, frequency is the reciprocal of that. Then in all your communication, you talk in terms of frequency only. Okay, similarly here, you will be talking in terms of a reciprocal space called K space. So we'll start that in the next chapter. So meanwhile, go through this, get this clarified. If you have any doubt, you can always message me. Okay?
Okay.
Yeah. Okay, good day then. I'll stop the recording.
Bye.
Yeah.